In this video, we will define what semiconductor is. We can classify solids according to their energy band structure. In this classification, solids are classified into largely two categories: metals or electrical conductors and insulators. In a typical energy band diagram for a metal, you typically have a one continuous energy band in which electrons fill up to a certain point. So you have a one large band that is partially filled with electrons. On the other hand, typical energy band diagram of an insulator looks like this in the figure in the left, and it features two bands: conduction band above the band gap and valence band below the band gap. And in between, there is a region of energy that is forbidden, which we call band gap. And in the lowest energy configuration, that is T equals 0, absolute temperature, electrons fill up the entire lower band, valence band, and the conduction band remain completely empty. This is a feature of an insulator. So, the presence of a band gap is important. However, the mere presence of band gap doesn't necessarily mean you have either metal or insulator. The electronic configuration or occupation of electrons of these bands at its lowest energy configuration is what determines whether a certain solid is a metal or an insulator. So, to make that more understandable, I'll give an example of a water bottle. If you have a water bottle that is partially filled, as shown here in this example, and if you tilt it, then you will have a water flowing in the direction that the bottle is tilted. And just like that, if you have a partially filled energy band, and if you tilt it, in this case, it is the application of external electric field that acts as tilting here, then the electrons will flow according to along the direction determined by your electric field. This makes the solid a good conductor. So, if you have a solid whose band structure features at least one partially filled band, then you have a metal, and you have a good conductor. On the other hand, if you have a completely full band, as shown here in the example of completely full water bottle, then even if you're tilting the bottle, there will be no net flow of water because the bottle is already full. There is no place for the water to flow. And just like that, if you have a completely full band, then even as you apply electric field, there will be no electron flow because there are no empty states that the electron can go into. If you have a completely empty band, of course, then there are no charge carriers, and therefore there will be no current. This is a feature of a good electrical insulator. So what is a semiconductor then? Semiconductor is a kind of an insulator whose band gap is small enough. Okay? What is small enough then? Typically, it is 2 to 3 electron volt. There is no scientific definition of this limit. This is all empirical. Some people call it a wide band gap semiconductor. Then other people might call it an insulator, and vice versa. The typical energy band gaps for semiconductors are listed here. Indium antimonide has a band gap of 0.16 electron volt. Germanium has a 0.67 electron volt. And these types of semiconductors are called a narrow band gap semiconductor. Silicon and gallium arsenide has a band gap of around 1.1, 1.4 electron volt. These are sort of the typical energy band gaps for semiconductors. And there are semiconductor that has a larger band gap: gallium phosphide with 2.2 eV, gallium nitride 3.5 eV, zinc sulfide around 3.7 eV. These are called a wide bandgap semiconductor. So here I introduce a rigorous scientific definition of semiconductor. Semiconductor is a solid that is an insulator at T equals 0 Kelvin, but whose energy band gap is such a size that thermal excitation at finite temperature leads to an observable change in conductivity at temperature below its melting point. These guys are called a semiconductor. So here is an energy band diagram, simple energy band diagram. Metal may or may not have a band gap. In this case here, there is a band gap. In this case here, there is no band gap. But in either case, it features at least one partially filled energy band. In the figure shown left here, the lower band is partially filled. In the figure on the right here, labeled B, there is no band gap, one big energy band that is partially filled. In both cases, there is at least one partially filled energy band. This makes this solid metal or good conductor. On the other hand, you have an insulator which has a valence band and conduction band separated by a band gap at the lowest possible temperature. Then insulator has a band structure where the valence band is completely full with electrons. Conduction band is completely empty. Now, what about at finite temperature? Then some of the electrons at the top of the valence band may have enough thermal energy to overcome this energy band gap and jump across the band gap and show up in the conduction band. This may not happen at room temperature, at least, if this energy band gap is very large. So even at finite temperature, the solid will remain insulator. This is a feature of an insulator. If this energy band gap is reasonably small, then at room temperature or slightly elevated temperature, there will be a sizable fraction of electrons near the top of the valence band with enough thermal energy to overcome the band gap and show up in the conduction band. If that happens, you now have two partially filled bands. Valence band is partially filled, conduction band is also partially filled, and both of these two energy bands can then contribute to electrical conductivity. So semiconductor is different than metal in that there are two types of conductivity arising from conduction band and valence band. In the case of metal, there is only one partially filled energy band, and there is only one band that is responsible for electrical conductivity, and that is a fundamental difference between the conduction in metal versus conduction in semiconductor. Now, let's consider electrical current. Electrical current is defined as the movement of charge carrier. So total current density J is simply a summation of the charge individual charge carrier carries and its velocity. If you sum these Q times V product for all electrons in your system, that is your total electrical current density. Semiconductor, as I mentioned, has a two partially filled band. So in the conduction band, you basically have electrons which carries a negative Q. Q here is the electronic charge, 1.6 times 10 to the negative 9th coulomb, and multiply that with its velocity, Vi, and sum this product over all electrons in the conduction band, and that is the current density in the conduction band. For valence band, we can do the same. You can sum these negative Q times V sub I product for all electrons in the valence band, and that will be the electrical current density due to valence band. However, as you see in the previous figure, the valence band is full except for some small fraction at the very top. So the summation will be very large, and computationally it will be very difficult. So if we have a simpler description that allows us to do the summation more easily, that will be beneficial, and that is the concept of hole. In other words, total current density in the valence band is the summation of the product negative Q, electronic charge, times its velocity for all of the electrons in the valence band. Now, that can be rewritten as the difference between the summation over all states, empty or occupied, minus the same products summed over empty states. Now, the summation over all states, this is the conductivity of a full band. And as I said, the full band, if the band is completely full, electrons cannot move. There are no empty states that electron can move to. So this first term here will be 0, and you're left with only this last term here. Now, because there is a negative sign here, the charge, the sign in front of your Q changed to a positive sign. So this is an expression for a charge carrier that carries a positive charge. Now it is summed over empty states, so there is no real particle. We're just summing over empty states, electronic state that is not occupied by electron. However, the current behavior due to this is very similar, mathematically identical, to the current density induced by a positive charge carrier. So we call this positive charge carrier, which is fictitious, holes, and typically we describe the conductivity arising from the valence band electrons as a movement of these fictitious positively charged carriers called holes. So in semiconductor, there are two types of electrical current, one arising from electrons in the conduction band and another arising from holes in the valence band. Now, effective mass. Electrons in a semiconductor behaves as if it is a free carrier, free electrons, moving in the free space, except that it has a different mass. So the effect of the atoms inside the solid, which must influence the electron's movement, is described as this quantity called effective mass. The collective influence of atoms in solid is described by this different mass. And the effective mass is a consequence of an energy band structure and is defined by the curvature of the energy band. So if you have a simple free space electron, the energy of free space electron is entirely kinetic energy. And so if you plot energy versus K, then the curvature is inversely proportional to M, as shown here. And if you plot the energy band structure of a semiconductor, energy versus K vector, then you will see a lot more complex behavior, but near the band edge, near the top of the valence band shown here, and near the bottom of the conduction band shown here, you can approximate this small region with a parabola and apply this equation here for the free space electron. And if you take the inverse of this curvature of the conduction band, you get the effective mass of electron in the conduction band. If you take the inverse of the curvature of this valence band, there are several different valence bands here, and they give you effective mass of holes in the valence band. And these are some of the examples of effective masses in some representative semiconductors. Germanium, silicon, and gallium arsenide, these are the band gaps. Small band gap, medium band gap, slightly higher band gap. And the effective masses are shown here. In the case of gallium arsenide, the energy band structure is isotropic, meaning the direction of K vector is not, the energy band structure, or the curvature of the energy band structure, is independent of the direction of the K vector. So you get a nice single scalar value for effective mass. For silicon and germanium, the energy band structure is different for a different direction of K vector, and that requires some sort of an averaging scheme to get a single number for effective mass. And depending on what you're calculating, we use a different method of averaging for these different directions, effective masses for different directions. So for density of state calculation, we will discuss this later in detail. We use harmonic mean of the effective mass for different directions. And for the conductivity calculation, we use a geometric mean of effective masses.